Welcome! Today, we're exploring a fascinating convergence of fields: material science, manufacturing, and artificial intelligence. We'll be looking at how we can literally print electronic devices and how AI is making that process smarter, faster, and more powerful.
For decades, the electronics that power our world, the chips in our computers and phones, have been built on silicon, fabricated in ultra-clean, highly complex facilities using processes like lithography. This approach has given us incredible processing speeds, but it has its limitations. The future demands electronics that are flexible, stretchable, even wearable. We need devices that can interface seamlessly with irregular surfaces, including the human body. This is where the field of printing electronics comes in. It's an emerging set of techniques used to create devices like flexible displays, transistor arrays, solar cells, and biosensors. Traditionally, this has involved low-cost processes like inkjet printing, roll-to-roll manufacturing, or tape casting. But the rise of additive manufacturing, what we commonly call 3D printing, has opened up a world of new opportunities for creating electronics in automated and highly customizable ways. Imagine for a moment how we typically manufacture a battery. It's a multi-step, complex process: preparing a slurry, casting it onto a tape and drying it, calendaring or pressing it, cutting the electrodes, packaging it all together, and finally filling it with an electrolyte. With printing, this entire streamline can be dramatically simplified. The process is narrowed down to designing the electrode and electrolyte pattern, preparing the specialized filament or ink, printing the components layer by layer, and then packaging the final device. This shift offers incredible designer freedom and can significantly reduce manufacturing costs. Now, let's add another layer to this: artificial intelligence. By coupling the automation of printing with AI, we can build digital twins of our devices, use machine learning algorithms to optimize the printing process in real time, and even drive new scientific discoveries. This combination is poised to help us tackle major societal challenges in healthcare, energy, and beyond. In our discussion today, we'll first explore the landscape of printing electronics in general. Then we'll focus on the exciting progress in 3D printing of specific devices like supercapacitors, sensors, batteries, and fuel cells. And finally, we'll examine the crucial role that AI is beginning to play in this revolution. It's important to note that our focus will be on what are called non-lithographic printing methods, techniques where a material or ink is transferred directly, rather than processes that involve etching or traditional photolithography.
Let's begin by looking at the broader field of printing electronics. The growing importance of this area is clear from the scientific literature, which shows a steady and significant rise in publications on printable electronics over the last 15 years. When we look at the materials driving this trend, we see a high popularity of inks made from 2D materials, metal nanoparticles, and metal oxide nanoparticles.
Printing methods themselves can be divided into two main categories: contact and non-contact printing. Contact printing involves direct physical contact between the printing apparatus and the surface. These methods can be distinguished by the relative positioning of the printing and non-printing areas. For example, in screen printing, the printing areas are flat and ink passes through a pre-patterned mesh screen. In gravure printing, the printing areas are engraved below the surface. And in flexography, a flexible relief plate is used, where the non-printing areas are below the printing surface. Non-contact printing techniques, however, deposit material without direct contact. Let's look at a few key examples. Inkjet printing uses a small nozzle, typically around 20 microns, to eject tiny, non-viscous droplets onto a substrate. Aerosol jet printing uses a much larger nozzle, perhaps 100 to 300 microns, and relies on a carrier gas to bring an atomized ink from a reservoir to the printhead, where a sheath gas then focuses it into a fine stream. Extrusion-based printing, which we'll see as foundational for much of 3D printing, pushes a filament of material through a heated liquefier and a nozzle. Finally, there's electrostatic printing, a particularly interesting technique. Here, an electric field is used to create a surface tension-limited meniscus of ink, from which downsized droplets are drawn and precisely guided to the substrate. The nozzle sizes here can range from 100 microns all the way down to just 0.2 microns. Electrostatic printing and a related technique, electrospinning, are becoming very important for next-generation energy and medical applications.
Both use electric fields to manipulate and extrude materials. Electrospinning is a well-established process that generates nano to sub-micron scale fibers, forming a membrane with high porosity and a large surface area. Electrostatic printing, by contrast, is a younger technology, but offers the ability to deposit materials with much greater precision and control. While commercial electrospinning equipment is readily available, the electrostatic printer is still in its infancy, but it holds great promise for fabricating electronics with fine, controlled patterns. These electrospun nanofiber membranes have found broad applications in soft electronics, being used in sensors, photodetectors, and transistors, thanks to their large surface area and flexibility. In the realm of energy storage, they have been used to create tubular carbon networks for better battery electrodes, to act as fillers to enhance ion conductivity in solid electrolytes, to form porous, flexible membranes for high-performance separators, and even to create 3D host structures for advanced battery chemistries like lithium metal and lithium sulfur.
This brings us to the next evolution: full three-dimensional printing of electronics. Additive manufacturing builds objects one layer at a time, using techniques like material jetting, extrusion, powder fusion, and photopolymerization. Compared to traditional subtractive manufacturing, where you carve material away, additive manufacturing is far less reliant on complex supply chains and tooling, and it excels at creating objects with complicated geometries and a high degree of customization. Using these methods, we can manufacture a wide array of electronic components: transistors, diodes, multi-layer circuits, solar cells, antennas, and, as we'll now explore in more detail, energy storage devices like supercapacitors and batteries. Let's start with supercapacitors. These devices are known for their excellent power density and long cycle life. With printing, we can create flexible, lightweight, and safe supercapacitors by printing custom-designed current collectors, substrates, electrodes, and even the electrolyte materials. For instance, one group demonstrated a solid-state paper-based supercapacitor by printing carbon nanotubes, an ionic liquid, and a photocross-linkable polymer electrolyte.
Another compelling example involves enhancing activated carbon with catechin hydrate and then printing an electrolyte based on a deep eutectic system. The manufacturing process is elegant in its simplicity. It begins with a polylactic acid film as the substrate. First, a graphite ink is printed to form the current collector. Next, an ink made of the catechin-grafted activated carbon is printed on top to form the electrode. Finally, the deep eutectic system, or DES, is 3D printed to act as the electrolyte. Two of these are then assembled with a separator in between to form the complete symmetrical supercapacitor. The charge storage mechanism in this device relies on the redox reaction of hydroquinone and quinone groups on the surface of the carbon. This device achieved a capacitance of 75 farads per gram and 90% cycling stability after 10,000 cycles. To continue advancing supercapacitors, 3D printing techniques will need to be further adapted to create the highly porous structures needed for high capacitance and large mass loading. Next, let's consider sensors. While our current world is filled with rigid sensors made from silicon, the future of healthcare and the Internet of Things requires flexible sensors. 3D printing is a perfect tool for this. For example, researchers have demonstrated that you can 3D print an interdigital sensor for detecting salt and sucrose concentrations using a commercially available conductive polymer filament. The sensor has a simple layout, with two interlocking comb-like electrodes on an insulating substrate. The entire structure, with a gap of just 2 millimeters between the fingers, is printed in a single process. When connected in a simple circuit with a voltmeter and a DC power supply, this printed sensor can measure changes in the electrical properties of solutions, allowing it to sense different concentrations of salt and sucrose.
Now, let's turn to batteries. Printing can enable safer, more environmentally friendly, and flexible forms of energy storage. This is especially useful for miniaturized electronics, implantable medical devices, and the vast network of sensors that will form the Internet of Things. Using techniques like direct ink writing, fused deposition modeling, and stereolithography, researchers are creating batteries with greater design freedom and higher energy densities. One team developed a multi-process approach to 3D print sodium-ion batteries.
They use direct ink writing for the positive electrodes and a technique called vat photopolymerization for the gel polymer electrolytes. These printed batteries showed impressive room temperature ionic conductivities and a wide stability window of 4.8 volts. In another study, direct ink writing was used to fabricate planar, flexible sodium-ion microbatteries. These devices with microelectrodes up to 1,200 microns thick delivered a high aerial capacity and maintained their performance for over 6,000 cycles. Beyond batteries, 3D printing is also becoming a transformative technology for fuel cells. Amid a global surge of interest in hydrogen as a clean energy carrier, fuel cells are being developed for heavy-duty transportation like trucks, trains, and even airplanes. 3D printing helps overcome many of the challenges in fuel cell manufacturing. It allows for the creation of intricate parts like proton exchange membranes and gas diffusion layers with high precision. For example, 3D printed flow field plates, a key component, can be designed with optimized channel structures to ensure an even distribution of reactant gases, which reduces energy losses and enhances the fuel cell's performance. Additive manufacturing also enables the design of lightweight, compact parts, which is critical for automotive and aerospace applications, where space and weight are at a premium. The ability to use various materials, metals, ceramics, polymers, offers the potential for highly durable and corrosion-resistant components. A powerful example of this comes from a study on solid oxide cells. Researchers used advanced ceramic 3D printing methods like stereolithography to fabricate large area cells. The electrolyte, made of yttria-stabilized zirconia, was printed with an advanced honeycomb geometry for enhanced performance. In fuel cell mode, these cells generated up to 3.5 watts of power, and impressively, in a long-term test running for over 1,150 hours at 900 degrees Celsius, the cells showed minimal degradation. It's worth noting that traditional printing methods like screen printing have also been successfully used to fabricate the electrodes and electrolytes for solid oxide fuel cells.
So we see that 3D printing is a powerful tool for creating complex, functional electronic devices. But how can we make this process even better? This is where artificial intelligence enters the picture. Machine learning can be combined with printing and additive manufacturing to dramatically enhance efficiency. AI can be applied at every stage of the process, from initial planning and design automation to predicting the properties of the final product to real-time process monitoring and optimization, quality control, and even defect detection. Imagine in situ customized additive manufacturing using bioelectroactive inks and open-source AI algorithms to create wearable and smart biosensors at a fraction of the current cost. This is the future AI can help build. When we look at how AI models are currently being used to enhance 3D printing, the data shows that the single largest area of application, at 42%, is in process optimization. This makes sense. For a printing process like fused deposition modeling, parameters like nozzle temperature, flow rate, and pressure are critical. For powder bed fusion, laser power and scan speed are key. Getting these parameters right is essential for a successful print. Other important applications of AI include predicting the final properties of the printed part, such as its mechanical strength or surface roughness, as well as optimizing simulations to reduce computational costs. One of the most common tools used is the artificial neural network, or ANN. For instance, researchers have used an ANN to predict the final dimensions of a 3D printed cylinder. The model takes the FDM machine settings as its inputs, features like the slice thickness, the air gap between printed lines, the deposition angle, and the bead width. The neural network then processes this information through its hidden layers to predict the output, the percentage difference in the length and diameter of the final printed part compared to the original design. Looking at the broader landscape of AI methodologies used in the literature, we see that about 42% of applications fall under the general category of machine learning, which includes regression and classification models. The other major players are all forms of deep learning. Convolutional neural networks, or CNNs, make up 28% of applications. Artificial neural networks, like the one we just discussed, account for 24%. We also see smaller but significant use of more advanced architectures like generative adversarial networks, GANs, which are excellent for unsupervised learning, and recurrent neural networks, like LSTM, which are designed to process sequential data, making them ideal for monitoring a process over time. Perhaps the most exciting development is the creation of fully AI-automated 3D printing systems.
One team developed what they call a Bayesian Experimental Autonomous Researcher, or BEAR. This system combines high-throughput automated experimentation with Bayesian optimization. The physical setup consists of 5 3D printers, a 6-axis robotic arm to move samples, a high-precision scale, and a universal testing machine to measure mechanical properties. The goal was to find the printing parameters that would maximize the toughness of a specific component, a crossed barrel structure. Instead of manually testing every possible combination of parameters, a grid search that would take thousands of experiments, the AI takes over. The system prints a component with a certain set of parameters, the robot moves it to the testing machine, which measures its toughness. This result is then fed back to the Bayesian optimization algorithm.
This algorithm intelligently decides which set of parameters to try next. Initially, it might explore parameters where the uncertainty is highest, a strategy called maximum variance. But as it gathers more data, it shifts to a strategy called expected improvement, testing parameters that it predicts are most likely to yield a better result than the best one found so far. The visualization of this process shows the AI quickly zeroing in on the most promising regions of the parameter space. The result of this approach was a staggering 60-fold reduction in the number of experiments needed to find the optimal parameters for maximizing toughness, all achieved with a very limited amount of initial experimental data. This demonstrates the power of autonomous, AI-driven research. We expect that similar approaches will soon benefit the field of electronics printing and optimization. The implications of this AI-driven approach are vast. For both additive and subtractive manufacturing, material properties and processing parameters need to be optimized. This can be automated by machine learning. Developing new sensors will require materials with specific optimized properties, often created from hybrid materials. AI and machine learning methods will be essential for designing these new materials and their compositions, tailoring their properties, their dynamic responsiveness, and their processability. By using digital twins and automated workflows for material selection and design, we can significantly reduce the time and cost for developing future electronics. For example, AI has been used to formulate 3D printable composites with up to 91% filler material, to model the interfacial properties within a composite sensor, and to guide the 3D printing of piezoelectric composites with boosted sensing behavior. These AI-aided design and fabrication routes are opening the door to a new generation of high-performance, flexible, and wearable devices. In conclusion, printing electronics and artificial intelligence represent a natural and powerful combination, perfectly suited for our advancing world of the Internet of Things, Industry 4.0, and smart manufacturing. The continued interaction between these two fields will undoubtedly spark new inspiration for a more personalized, environmentally friendly, and energy-efficient future. The recent advances we've discussed today in both the printing techniques and the AI algorithms that guide them are laying a critical foundation for the machine learning-driven manufacturing of the flexible electronics, supercapacitors, batteries, sensors, and fuel cells of tomorrow.